Welcome to Podcast Learn and Fun. Let's start today's journey of learning. Okay, so today we're looking at density operators in quantum physics.
Yeah.
And I know that might sound kind of intimidating,
Right.
but it's actually pretty cool stuff.
It is, yeah.
Once you get the hang of it, it's all about how we describe these quantum systems, which, can be a bit fuzzy and uncertain compared to like the everyday world that we're used to.
Right. You see, in quantum physics, we don't always have perfect information about a system. Sometimes we know the exact state it's in.
Okay.
Like knowing for sure that an electron has a specific spin.
Right.
We call this a pure state.
So it's like if you had a coin balanced perfectly on its edge,
Exactly.
you know exactly what state it's in. You have 100% certainty.
Exactly. But often things are messier.
Okay.
We might have a bunch of electrons and only know the probabilities of them having different spins. Maybe there's a 50% chance one electron is spin up and a 50% chance it's spin down. This is where mixed states come in. It's like flipping that coin. You don't know the outcome until you look.
Ah, I see. So pure states are like knowing the coin is on its edge, while mixed states are like flipping it and having that uncertainty.
And here's where density operators become our heroes.
Okay.
They give us a way to mathematically represent both pure and mixed states, all in one framework. Think of it like this. For a pure state, the density operator is like a spotlight shining brightly on that one specific state.
Okay.
But for a mixed state, it's more like a dimmer switch, spreading the light across multiple states with the brightness over each state representing its probability.
Okay, I think I'm starting to get the picture. So density operators help us capture this essential fuzziness that's baked into the quantum world.
And not only that, they have some pretty neat mathematical properties that make them even more useful. For example, one key property is called hermiticity.
Okay.
Without getting too technical, this basically means the density operator is its own mirror image in a mathematical sense.
Right.
This ensures that when we use it to calculate physical quantities, we get results that make sense.
Okay.
Real numbers that reflect what we observe in the real world.
So it's like there's a built-in safeguard that keeps the math grounded in physical reality.
Precisely. Another crucial property is positivity.
Okay.
This ensures that when we use density operators to calculate probabilities, those probabilities are always positive numbers, as they should be.
Right.
You can't have a negative chance of something happening.
Right.
These properties, along with a few others, make density operators incredibly powerful and consistent tools for describing quantum systems.
It sounds like density operators are really essential for working with quantum systems, especially when we don't have complete information.
Yeah.
But how do we actually use them to make predictions?
Right.
Like, how do we calculate the probability of getting a specific measurement outcome?
Well, imagine you're finally ready to look at that flipped coin. The density operator lets us predict the chances of seeing heads or tails. We can use it to figure out the probability of finding the system in a particular state when we make a measurement.
So it's like we're peering into the future, but with a quantum twist. We're not predicting the exact outcome, but rather the probabilities of different possibilities.
And what's even cooler is that density operators can also help us understand how these probabilities change over time. The density operator itself evolves over time, guided by the system's energy, what we call the Hamiltonian. It's like predicting how that spinning coin will eventually settle down, either on heads or tails, by understanding the forces acting on it.
So it's not just about static probabilities, but about how those probabilities shift and change as the quantum system interacts with its environment.
Exactly. It gives us a dynamic picture of the quantum world, allowing us to see how these systems evolve and behave over time.
This is all so fascinating. But how can we tell if we're dealing with a pure state or a mixed state just by looking at the density operator? Is there some sort of telltale sign?
There is. It's all about a concept called purity. Think of it like this. A pure state is perfectly sharp and well-defined, like our coin standing on its edge. Its purity is 1. A mixed state, on the other hand, is always a bit fuzzy, like that flipped coin. Before we look at it, its purity is always less than 1.
So the purity tells us how much uncertainty is mixed into the system state. The lower the purity, the less we know for sure. That makes sense. But in the real world, wouldn't most quantum systems be in mixed states? After all, they're constantly interacting with their surroundings.
You hit the nail on the head. Pure states are often an ideal simplification. In reality, most quantum systems are constantly bumping into other particles, exchanging energy, and generally getting entangled with their environment. This leads to those fuzzy mixed states. And that's why density operators are so powerful. They allow us to handle the messiness of reality, not just idealized textbook examples.
So it's like density operators are the tool we need to bridge the gap between the pristine quantum world and the messy world we actually live in.
Precisely. Now, you might be wondering, where do we actually see density matrices being used in the real world? Well, one of the most exciting areas is quantum computing.
Ah, yes. Quantum computers. I've heard they're going to revolutionize everything from medicine to material science. But I must admit, I find the whole concept a bit mind-boggling. How did density operators fit into this picture?
They're essential. You see, the building blocks of quantum computers are called qubits. Think of them like the bits in our classical computers, which can be 0 or 1. But qubits can be in a superposition, a blend of both 0 and 1 at the same time. And guess what? Density operators are perfect for describing these superpositions. They can capture the fuzziness of a qubit being in multiple states at once.
Wow, so density operators can handle the strangeness of quantum mechanics, allowing us to describe and manipulate these superpositions that are at the heart of quantum computing.
Exactly. And what's even more amazing is that they can also describe entanglement, this spooky connection that can exist between two or more qubits. It's like they're linked together in a way that defies our classical intuition.
Entanglement. That's the one where two particles can be light years apart, but they're still somehow connected, and what happens to one instantly affects the other?
That's the one. And density operators provide the mathematical framework to model and understand this phenomenon. It's crucial for harnessing the power of entanglement for things like quantum cryptography and quantum teleportation.
This is mind-blowing. It seems like density operators are not just a theoretical tool, but are really paving the way for these revolutionary quantum technologies.
They absolutely are, but they're not just useful in the quantum realm. Remember how we talked about mixed states arising from interactions with the environment? Well, this is where another key concept comes in: decoherence.
Decoherence, that sounds ominous. Is that a bad thing?
It can be. It's basically the process where quantum systems lose their quantumness and start behaving more like classical systems, the kind we're used to in our everyday world.
So it's like the magic of quantum mechanics is fading away, like the coin finally settling on either heads or tails.
A perfect analogy. And guess what? Density operators help us understand this process, too. We can use them to track how a quantum system loses its coherence, its delicate superposition, as it interacts with its environment.
So density operators are kind of like a window into this transition zone between the quantum world and the classical world.
Precisely. They allow us to study this boundary to see how the strangeness of quantum mechanics gets washed away as systems interact with their surroundings.
This is giving me a whole new perspective on how we experience reality. It's like there's this underlying quantum layer that's always there, but it gets obscured by decoherence as we move to larger and larger scales.
That's a great way to put it. And density operators are helping us unravel this fascinating interplay between the quantum and the classical.
All this talk about decoherence is reminding me of something else: thermodynamics and statistical mechanics. Those fields are all about how the behavior of large groups of particles leads to the macroscopic properties we observe.
You're making a great connection. Density operators are actually deeply intertwined with statistical mechanics. In fact, they provide the foundation for describing quantum systems at thermal equilibrium. Think about it. If you have a large collection of atoms in a gas, it's practically impossible to track the exact state of each individual atom. But we can use a density operator to describe the overall statistical distribution of states for the entire system.
So it's like we're using density operators to zoom out and look at the forest instead of getting lost in the trees.
Exactly. We can say things like, on average, this percentage of atoms are in this energy state and that percentage are in that energy state, even if we don't know the exact state of any particular atom.
This is really starting to paint a picture of how density operators are this incredibly versatile tool that connects so many different areas of physics: quantum mechanics, statistical mechanics, thermodynamics, and even cosmology. It's like they're a unifying thread running through all these different areas. It's incredible how density operators can bridge these different scales from the microscopic world of atoms and qubits to the macroscopic world of gases and stars.
And that's just the tip of the iceberg. We're constantly finding new and surprising applications for density operators. For example, they're now being used to model complex systems in chemistry, biology, and even finance.
Wow. I never would have imagined that something from quantum physics could have implications for things like stock market predictions.
It's a testament to the power of these mathematical tools. They allow us to model and analyze systems with a level of detail and sophistication that was simply not possible before.
This has been an amazing journey into the world of density operators. Before we wrap up, I wanted to ask you, where do you see this field going in the future? What are some of the big unanswered questions or exciting frontiers that density operators might help us explore?
That's a great question. One area I'm particularly excited about is the role of density operators in understanding the very early universe. You see, in the first moments after the Big Bang, the universe was incredibly hot and dense, and quantum effects played a dominant role. Density operators could be key to unraveling the mysteries of that era and understanding how the universe evolved into what we see today.
So it's like we're using these tools to peer back in time to the very beginning of everything.
Exactly. Another exciting area is the development of new quantum technologies. As we build more powerful quantum computers and other quantum devices, we'll need increasingly sophisticated theoretical tools to describe and control them. Density operators will undoubtedly play a central role in that endeavor.
It sounds like we're just at the beginning of exploring the full potential of density operators.
Absolutely. We're still discovering new and surprising ways to apply these tools, and I have no doubt that they will continue to lead to groundbreaking discoveries and innovations for many years to come.
This has been an incredibly illuminating conversation. I feel like I've gained a whole new appreciation for the power and beauty of density operators. Thank you so much for sharing your insights with us today.
It's been my pleasure. I'm always excited to talk about the wonders of quantum mechanics.
Thank you for listening to Podcast Learn and Fun. If you like our videos, please subscribe, click the like button, comment, and share. See you next time.